Today we are going to explore a fascinating concept in physics called Pascal's principle. In this lesson we have three main goals. First, we will define Pascal's principle. Second, we will understand how pressure is transmitted in liquids. And finally, we will learn how to solve basic hydraulic problems. By the end of this lesson, you will be able to explain how a small push can lift a heavy car and solve problems involving hydraulic systems. To understand how hydraulics work, we first need to define a fundamental concept in physics: pressure. In physics, pressure is defined as the amount of force applied over a specific area. Think about pressing your thumb against a wall versus pressing your whole palm with the same strength. Your thumb feels more pressure because that force is concentrated on a much smaller spot. We write this as pressure P equals force F divided by area A. The standard unit for pressure is the Pascal, or newtons per square meter. Now that we know what pressure is, we can see how it behaves inside a liquid. Now, let's look at the core idea of today's lesson: Pascal's principle. Pascal's principle states that when you apply pressure to a fluid that is trapped in a container, that pressure is passed on, undiminished, to every single part of the fluid and the walls of the container. Notice how the arrows are the same size everywhere. Unlike a solid object, where a push mostly moves things in one direction, a liquid spreads that push out in every direction simultaneously. Because liquids are almost impossible to compress, they are perfect for moving energy from one place to another. This is the secret sauce behind how heavy machinery works. Let's see how we can use this principle to lift something heavy, like a car, using a hydraulic system. A hydraulic system usually consists of two pistons connected by a tube filled with oil or water. We call the smaller one the master piston, and the larger one the slave or ram piston. When we apply a small force, F1, to the small area A1, we create a pressure in the fluid. According to Pascal's principle, this exact same pressure, P, travels through the fluid to the large piston. Because the area, A2, is much larger, the fluid has a much bigger surface to push against. Since the pressure is the same at both ends, we can set these two formulas equal to each other. This means that a small force on a small area can create a massive force on a large area. It's like a force multiplier. The hydraulic lift is a fundamental tool in engineering that allows us to move heavy loads with minimal effort. Let's try a mathematical example to see this in action. Suppose we have a hydraulic press, where the larger piston is 10 times the size of the smaller one. If the smaller piston has an area A, and the larger piston has an area of 10 times A, what happens when we push down with a force, F? We know the pressure must be the same throughout the liquid. So, the pressure created at the first piston, which is force over area, must equal the pressure pushing up on the second piston. We can set up our equation: F divided by A equals the second force, F2, divided by 10 times A. When we solve for the second force by multiplying both sides by 10A, the A terms cancel out. We find that the output force is 10 times the input force. This means if you push with 100 newtons of force, the machine pushes back with 1,000 newtons. You've effectively made yourself 10 times stronger. Where do we actually see this in the real world? Hydraulics are everywhere, making difficult tasks much easier. From stopping your car to lifting heavy equipment. Here are some common uses. First, think about car brakes. When you tap the brake pedal with your foot, you aren't strong enough to stop a 2-ton car moving at high speed. But because of Pascal's principle, that small force from your foot is transmitted through the brake fluid and magnified at the wheels to clamp the brakes shut. Hydraulic jacks work the same way. By pumping a small handle, you use a small piston to gradually lift a heavy vehicle. Even at the dentist or the barber, when they pump a lever with their foot to raise your chair, they are using hydraulics to lift your weight smoothly and effortlessly. And for big machines like airplanes, hydraulic systems are used to retract and extend the heavy landing gear against the strong force of the wind. In all these cases, we use a small, manageable force to control a very large one. Let's practice with a more detailed calculation. This problem asks us to find the pressure and the area in a specific hydraulic setup. We are given an input force of 40 newtons applied to a pump piston with an area of 2 square centimeters. We want to lift a heavy load of 1,000 newtons. First, let's find the pressure being transmitted through the system. Using our formula, pressure equals 40 newtons divided by 2 square centimeters. This gives us 20 newtons per square centimeter. If we convert this to standard units, it's equivalent to 200,000 newtons per square meter, or 200,000 pascals. Now, since Pascal's principle tells us this pressure is constant, we can find the area needed for the larger ram piston to lift the 1,000 newton load. We set the pressure, 20, equal to the output force of 1,000 divided by the unknown area, A2. Rearranging the equation, A2 equals 1,000 divided by 20. The result is 50 square centimeters. So, by using a piston that is 25 times larger, we were able to lift a weight that was 25 times heavier than the force we put in. For our final example, we will look at how to find the size of a piston when we know the forces involved. This is a common engineering task. In this scenario, we apply 200 newtons to a master piston with an area of 25 square centimeters. The goal is to produce an output force of 5,000 newtons. First, we calculate the pressure created by the master piston. 200 divided by 25 gives us 8 newtons per square centimeter. Now, we use that same pressure for the output side. 8 equals 5,000 divided by the new area. Solving for area, we get 5,000 divided by 8, which is 625 square centimeters. To convert this to square meters, we divide by 10,000, giving us 0.0625 square meters. If we want to know the actual size of the piston, we can find its radius. Assuming it is circular, area equals pi times radius squared. 625 divided by pi is roughly 199. Taking the square root, we find the radius is approximately 14.1 centimeters. We have now covered the fundamentals of fluid pressure transmission, how to calculate the forces involved, and seen how these principles make our daily lives easier. Great job!